All right, let's start going over our second homework then. So this is for Chapter 2, web assignment number 2. First question here, it's about this toy car rolling on a straight track. You're given an initial position, your initial velocity, constant acceleration, and then there's a second toy car. So first question is about when the two cars have equal speeds. What you want to do, what you want to consider for all of these parts here is that you are dealing with obviously two moving vehicles. One has no acceleration, is undergoing constant velocity, and then one is obeying with constant acceleration, or is moving with constant acceleration. So what you're looking at each of these times is you are looking for them, in this case, you want them to have the same speed at the same time. So you actually have two missing variables. Then define, of course, what it is. And then part C, at what time do they pass each other? So that deals with final position and time. And what you're really going to do is get two equations and set them equal. That's the basic idea. Okay? So when the cars have equal speeds, you're going to be looking to work with equations that have final velocity. Okay, now this one works great for the object that's accelerating. Let's think about what we know about objects that are not accelerating. We know that the velocity, let's see if I can write it under here, velocity equals displacement over time, and velocity is going to be equal to, oh wait a minute, do I really want that one? Let me think about that. No, you know what, never mind, not this one. We can actually work with both of these, right? One of them, this piece is going to drop out, right? But the other one, we're going to have all of it. So we have an equation for our initial velocity, 5.3 centimeters per second for the car that is not accelerating. So yeah, the VF will equal the VI. That's not a big deal. Set that equal to the conditions for the other car and solve, right? That'll then give you the time that you're looking for. You can use that to find the velocity for part B. For part C, again, you're working with, you're looking for time when the cars pass each other. Remember that passing each other, that's not velocity, that's final position. Okay, so in this case, what you're looking for is you're looking for your, delta x equals VIT plus 1/2 AT squared for the car that's accelerating. This needs to be expanded because you're not looking for delta x, you're looking for final position. Okay, and it's actually very important because notice you have an initial position, so you can't just use delta x. All right, so there's your accelerating car, and then, oh, now maybe Mrs. Grady is talking about the right stuff. Let's see if I can move this over a little bit. There we go. My tripod is not always behaving. For our car that is moving with constant speed, again, expand this out to xf minus xi. And so once you do that and do the rearranging, set the xf's equal to each other, or set the equations equal to each other, that will drop out xf, and solve for the piece you need, and then of course you can answer the next part of the question. Okay, I believe, I don't think you have to do that part, if I'm correct. All right, so that one's a little bit tricky because you're dealing with two vehicles that are moving, but hopefully that gives you a little bit of an idea of how to go about solving that. You obviously are missing two variables for each one, so you want to use two equations and have one of those variables drop out so you can solve for the other piece that you're missing. Okay, blocking the roads slows uniformly. Okay, right, this is a pretty straightforward kinematics question. You're given acceleration, you're given time, you're given distance, and you're looking for final velocity. So my suggestion is you want to take these and figure out, what they stand for, and then pick the proper equation. And if you're not sure what they stand for, the units are always a good clue. If you have meters per second squared, that's always an acceleration. Seconds is for time. Meters is for displacement, distance, or position, depending on how the question's phrased. And of course, this is talking about final velocity. Okay? Yeah, oh, wait a minute. My bad. With what speed does it then strike the tree? I already know what VF is. This thing is gonna stop, right? Skid marks ending at the tree. So I'm looking for VI here, aren't I? You always have to look for those things they're assuming you know or can understand from the question. Okay, number 3, Also, the same sort of deal. It's a matter of really just looking and pulling out your variables. Notice it's in miles per hour, and all of these are in meters per second. That means you got to do some converting here. You can either use dimensional analysis. I honestly don't have trouble if you want to go to Google and convert that. That's not a big deal. Brought to rest, of course, tells you your final velocity, and this is going to give you your time. Okay, and then pick your proper kinematic equation. All right, you're looking for acceleration here, so you want one that obviously has acceleration, that has initial velocity. You know the final velocity of 0, and there's your time. Plug and chug. And then solve for a delta x, and you should be set. This one, position after, and you're given different times. All right, so you're looking for delta x. You know you're looking for delta x, sorry. You know the time. What else do we know? We know if he's rolling gently off the top of a warm TV set, the idea here is that our initial velocity will be 0. And what else do we know? If he's free falling, we know that the acceleration will be equal to little g, so you can use it there. Okay? And then of course find the position, find the velocity, so you're looking for final velocity. Again, you're just using some kinematic equations for that. Nothing too crazy there. Okay, now I am no fool. I realize most of you will just check yes or no until you get it right. Okay? But let's think about this. Let's move that up so hopefully we can see it. Tacker at the base of the wall. Oh, the bell is going to ring. I guess I better go. All right. See me about this one if you're having trouble. Okay? So I'll look forward to seeing you if you can't get this one.